Niels Bohr was frustrated. Just a month earlier, his student Otto Frisch had been part of a dramatic discovery, the splitting of the uranium nucleus. Now, as Bohr ate dinner at the faculty club at Princeton, another physicist, George Plachek, called into question Bohr's understanding of these new results. Bohr co-developed the liquid drop model of the nucleus, which Frisch had used to show that fission was energetically possible. But according to Plachek, Frisch's latest results left the situation more confused than ever. In a January publication, Frisch had experimentally shown not only that uranium could be split, but that its neighbor on the periodic table, thorium, could also be split. However, the fission process for uranium and thorium appeared to be quite different. Both elements would split under bombardment of high-speed neutrons, but uranium would also split under bombardment of slow neutrons, while thorium would not. Bohr's liquid drop model, Plachek claimed, offered no possible explanation for this. Thorium and uranium should behave basically the same according to the model. Bohr, arguably the second most influential physicist of the 20th century behind Einstein, was stumped. Why would uranium and thorium behave so differently experimentally? As Plachek continued, a fragment of a solution came to Bohr. At risk of losing it, Bohr stood up and quickly left without saying a word. Sensing Bohr may be onto something, the physicist Leon Rosenfeld followed him out, careful not to disturb his concentration. Bohr trudged through the snow in silence to the Institute for Advanced Study where he was borrowing Einstein's office. Bohr quickly drew two identical curves on the blackboard, breaking pieces of chalk as he went. These curves represent the nuclear cross-section, or the probability of a nuclear reaction, as a function of the energy of the incoming neutron. Bohr's curves show the total cross-section, which includes the probabilities of different outcomes. The section on the right shows the probability of splitting under high-speed neutron bombardment. The hump in the center of the graph corresponds to the probability of neutron absorption followed by beta decay. This behavior had been observed experimentally. Both uranium and thorium had absorption resonance peaks around 25 electron volts. Bohr labeled the first graph thorium, but he didn't label the second graph uranium. He instead labeled it U-238. Bohr then turned to Rosenfeld and said, "Now listen, I have it all." 4 years earlier, it had been shown using mass spectrometry that naturally occurring uranium wasn't just one thing. It was primarily composed of the isotopes uranium-238 and uranium-235. Thorium, on the other hand, was essentially made up of all one isotope. What Plachek hadn't considered, and what Bohr hadn't realized until he was pressed, was that uranium-238 and uranium-235 would behave differently under neutron bombardment, according to Bohr's liquid drop model. When absorbing the incoming neutron, uranium-238 ends up with an odd number of neutrons, while uranium-235 ends up with an even number. As captured by the pairing term in Bohr's liquid drop model, an even number of neutrons means that all neutrons can form very stable pairs of overlapping wave functions. This additional binding energy in the configuration of uranium-236 means that absorbing the neutron releases around 6.5 extra mega-electron volts of energy when entering this configuration, which happens to be enough to induce splitting, even with a zero-velocity neutron. Taking this into account, Bohr drew a third curve, his predicted curve for how uranium-235 would behave under neutron bombardment. This time, the whole curve represented only one outcome: splitting. The reason natural uranium split under slow neutron bombardment, while thorium did not, was because uranium was not just one thing. Its isotopes behaved differently due to the subtle difference between an even and odd number of neutrons. Bohr wrote up his results and submitted to the physical review. What he didn't realize at the time was that he had found the perfect material to build the atomic bomb.